In 1909, Hans Geiger and Ernest Marsden directed beams of alpha particles at a gold foil. This was an experiment initially done to investigate some unexplained behaviour of alpha particles, but it led to very important discoveries about the structure of the atom. Nowadays, we know that alpha particles are a type of radiation consisting of 2 protons and 2 neutrons, and we'll learn more about these particles elsewhere. Scientists didn't know about protons and neutrons at the time, but they had deduced that alpha particles had similar properties to a helium ion. So they had a strong positive charge and a similar mass to helium. These particles were fired at a thin gold foil, where by foil we mean that it is only a few atoms thick. So what would the expected results of this experiment have been? Well, the plum pudding model suggested that the alpha particles would pass through the gold without being affected. Remember that this plum pudding model was how scientists explained the structure of the atom at the time. They believed that atoms consisted of electrons embedded in positive spheres of matter. Importantly, they believed that the mass and charge of the atoms were evenly distributed. So when the alpha particles were fired at the foil consisting of these atoms, they should have no effect on its path. There's no concentration of mass or charge strong enough to disturb the heavy alpha particle. It's like firing a bullet at a sponge cake. It would just pass straight through. However, they instead found some particles were slightly deflected, while a very small number bounced back. During the experiment, charged plates surrounding the foil and the alpha source would produce a signal where alpha particles hit them, letting Geiger and Marsden determine the paths they took. They found that most of the signals were directly behind the foil, showing that the alpha particles passed straight through as expected. But a few were deflected by small amounts. These were still detected on the other side of the foil, but their paths had been changed slightly. But stranger still, some had large deflections of more than 90 degrees, meaning they were detected on the same side of the foil as the alpha source. This completely contradicted the plum pudding model, since the gold atoms shouldn't have had any effect on the alpha particle at all. So how could we explain these results? Well, in 1911, Ernest Rutherford explained these observations by proposing a nuclear model for the atom. Rutherford was also the scientist that devised and supervised the alpha scattering experiment, though he didn't actually take part in the experiment itself. Here's a simplified version of the atomic model Rutherford proposed, based on the evidence now available to him. He theorised that atoms contained a small charged nucleus, which the electrons surrounded. This nucleus would be tiny compared to the atom as a whole, but would still contain almost all its mass. So the electrons are actually in empty space, rather than embedded in the rest of the atom's matter. In his original paper, Rutherford stated that this nucleus could potentially be positively or negatively charged. But later experiments showed this nucleus is positively charged. So it contains the positive charge that balances the negative charge of the electrons. For your exams, you wouldn't be penalised for saying that Rutherford always theorised the nucleus was specifically positively charged. But where did this idea come from? Let's see by looking back at the observations from the alpha scattering experiment and seeing how this model explains them. First, only a few alpha particles were heavily deflected by the nucleus, meaning it must be very small compared to the size of the atom. So let's imagine some alpha particles reaching an atom in the gold foil. According to the nuclear model, the atom has a small nucleus, but the rest is empty space. So this means that most of the alpha particles will pass through the atom unaffected, since they won't actually come into contact with anything in the atom. Only the particles that come into close contact with the atom's nucleus would be deflected by more than 90 degrees. In fact, since Geiger and Marsden found that only 1 in 20,000 particles were deflected this way, Rutherford could theorise that the nucleus is around 1/20,000th the size of the atom. More modern experiments have given much more accurate measurements for the size of the nucleus, though. But you won't need to memorise any of these values for your exams. Then, in order not to be knocked out of the atom by collisions, the nucleus must contain a large amount of mass. So Rutherford knew that the alpha particles had almost as much mass as an entire helium atom. So if the nucleus is enacting a strong force on these, then you'd expect it to be pushed back as well by this force. Nothing from the experiment suggested the gold atoms themselves were being affected by the alpha particles, though. So if the nucleus moves, it could only be by a little amount. So the nucleus must have a huge mass to not be affected by the forces deflecting the alpha particle. Modern experiments have since shown that the nucleus contains over 99% of the mass of an atom. And finally, the nucleus must be charged in order to also cause deflections of particles that pass close by it. Specifically, this would explain why there were so many more particles undergoing partial deflections compared to how many deflected by more than 90 degrees. So if we assume the nucleus is positively charged, then we'd see some alpha particles get close enough to the nucleus to have their paths bend slightly. This is because of the repulsive electrostatic forces they experience from the charge of the nucleus. At the time, Rutherford didn't discount the possibility that the nucleus could be negatively charged, and the alpha particles experienced attractive forces instead. Then the strong deflections would be due to them slingshotting around the nucleus.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!